Welcome to this video on thrashing and operating systems. In this presentation, we will understand what thrashing is, what causes it, how to identify it, and how to prevent it in order to maintain optimal system performance. Thrashing occurs when a computer system spends more time handling page faults than executing the actual processes. This results in a severe degradation of the system's performance. In such a scenario, the central processing unit, or CPU utilization, drops dramatically as the system becomes overwhelmed with excessive paging operations. Several factors can lead to thrashing. First, insufficient physical memory occurs when the total memory requirements of all active processes exceed the available physical memory, which forces the system to constantly swap pages in and out. Second, a high degree of multiprogramming, where too many processes compete for limited memory resources, leads to excessive context switching and page faults. Third, poor page replacement algorithms can repeatedly swap out pages that will be needed again in the near future. Finally, inefficient working set management can lead to unnecessary page faults due to failure to properly identify and maintain the working set of processes. Now let's discuss the symptoms of thrashing. A dramatically reduced CPU utilization is a primary indicator. You'll also notice an increased response time for applications, making the system feel slow. High disk activity occurs due to constant paging, as the system struggles to find the necessary pages on the disk. And the system may appear to freeze or become unresponsive as it is overburdened with page swapping. The working set model is a technique used to prevent thrashing. It ensures that each process has its essential pages in memory before execution. The formula here, W of t, delta equals the set of pages referenced in the time interval between t minus delta and t, defines the working set. Delta, also known as the window size, determines how many recent page references are included in the working set. Several strategies can be employed to prevent thrashing. The working set strategy involves only allowing a process to execute when its entire working set is in memory. You can suspend processes if necessary to free memory. Page fault frequency control monitors the rate of page faults and adjusts memory allocation to maintain an acceptable page fault rate. Load control limits the degree of multiprogramming based on the total memory requirements of all active processes. Locality-based memory management optimizes memory allocation by recognizing and exploiting spatial and temporal locality in process memory access patterns. Page replacement algorithms play a crucial role in thrashing prevention. Least recently used, or LRU, replaces the page that has not been used for the longest period of time, exploiting temporal locality by keeping recently accessed pages in memory. First in first out, or FIFO, replaces the oldest page in memory, regardless of usage patterns. While simple, it is more prone to thrashing. The clock algorithm, a more efficient approximation of LRU, uses a reference bit and a circular queue structure to track page usage. The working set algorithm directly implements the working set model by tracking pages accessed within a time window and ensuring they remain in memory, specifically designed to prevent thrashing. Let's consider a case study involving web browser memory usage. Modern web browsers with multiple tabs can consume large amounts of memory, and when physical memory is insufficient, the system may start thrashing. For example, opening more than 50 tabs in Google Chrome on a system with 8 GB of random access memory, or RAM, can trigger thrashing, especially with memory-intensive web applications. To address this, modern browsers implement tab sleeping, where inactive tabs are unloaded from memory to prevent thrashing, while maintaining the appearance of availability. In summary, effective thrashing prevention requires a combination of detection mechanisms, intelligent memory management, and adaptive resource allocation strategies to maintain system performance under varying workloads. Key detection methods include monitoring page fault frequency, tracking CPU utilization patterns, and observing disk input-output activity spikes. Implementation involves using the working set model, locality-aware page replacement, and dynamic memory allocation. Prevention strategies include controlling the degree of multi-programming, ensuring sufficient physical memory, and implementing process suspension or resumption. Optimization can be achieved by balancing memory allocation between processes, prioritizing critical processes, and implementing memory compression techniques. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.